Hey everybody, welcome to another session in the AI journey where today we're going to talk about forward propagation in neural networks. If you will refer to the previous video of why do you require neural networks, you can refer to that video and then look at this session if that gives you a background. Otherwise, if you know about it, you can just directly come to this video. So forward propagation is something where the neural network learns about, not learns, but then it basically computes the values of its nodes and then propagates these values forward in every single layer, right? And then computes the output. That's called as forward propagation. And then later it compares the generated output with the actual output and then computes the gradient. And then this gradient moves backwards. That's called as backward propagation, right? So today we'll talk about forward propagation in a simple single layer neural network. So let's go to the whiteboard. So we just saw that a neural network typically looks like this, right? Let's say we have a 4 nodes as the input, 1, 2, 3, and 4. This is the input layer. And the values of each of these nodes is like, say, x1, x2, x3, and x4, right? Then let's say we have a hidden layer with 3 nodes, 1, 2, and 3. So we also got to know that, and then the output layer is like this with 2 nodes, let's say, okay? So we also going to know that like each one of these is connected to each of these nodes in a fully connected network, right? So x1, x2, x3, x4 is connected by the weights, let's say w11, w12, w13, and w14, right? So it's a weighted product that looks like this. Basically, w11 x1 plus w12 x2 plus w13 x3 plus w14 x4. And then each of these nodes, we also have something called as a bias term, which is a constant value that is irrespective of any of these inputs. So like we add a bias called as plus b, all right? Right, so this is the value which is going to this node, all right? Where the weights are W11, W12, W13, W14, and the inputs are X1, X2, X3, X4, right? So with a bias, right? Similarly, for this node, we're also going to have the same 4 inputs going, but with 4 different weights. This time it's going to be W21, X1 plus W22, X2 plus W23, X3 plus W24, X4 plus B, right? So let's write this B as B1 and this one as B2. And similarly for the third node, it's going to be like this, W31 X1 plus W32 X2 plus W33 X3 plus W34 X4 plus B3, right? So these three are the values going to each of the hidden nodes. So if you try to write this in matrix format, right? How does this work? Like this. W11, W12, W13, W14, W21, W22, W23, W24, W31, W32, W33, and W34, right? Then multiplied by x1. Okay, what you're going to do is you're going to transpose this. No, I think it's already transposed, right? So the number of columns in this matrix, which is 4, equals the number of rows in this matrix, which is 4. So it's conformable for multiplication, right? So multiply this together and then plus B1, B2, B3, right? This is how you represent these three in the matrix form, right? So if you represent this one as a matrix, like say W, and this one as the vector X, and this one as a vector B, then it becomes WX plus B equals 0, right? That's kind of the equation in the matrix form, okay? So now we know about the values entering each of these nodes. Now what happens here is that there's something called as an activation function, which comes into place over here, each of these nodes. So what is an activation function? An activation function is basically used to convert a linear value to a non-linear value, all right? So typically the one used is a sigmoid activation function. We also have other two, we'll discuss them in another video. So how is a sigmoid activation function working? Sigmoid, the equation equals 1 divided by 1 plus e raised to minus x, right? Right? So this x is basically the value of each of these terms, right? So whatever this value is, this comes into x, and then the range of fx is going to be between 0 and 1, because a sigmoid basically looks like this, right? The lower bound is 0 and the upper bound is 1, right? So whatever might be the value of each of these terms, the final value going to each of these nodes is always going to be something between 0 and 1. And why is this important? Because if it's kind of, say, a decision-making node, right? Whether it's like a yes or a no decision, that decision basically gets triggered based on the value, the intensity of the value, whether it lies between 0 and 1. Whether if it's like say very close to 1, then the value is going to be yes. If it's very close to 0, then the decision is going to be a no, right? Something like that. So that's why a sigmoid function is basically important for that kind of decision making. And then eventually, finally, like whatever values you have here, let's say you have y1, y2, and y3, right? These are, say, the values after applying the activation function, right? Then in a similar way, you're going to have weights like, say, w2, let's say wa1, wa2, wa3. This is going to be one set of weights, and this is going to be another set of weights going to the output. And in a similar way, we're going to have such kind of an equation, matrix equation, right? And then these are going to be the final output. So there's going to be an activation function here as well, right? So how does this work? Just to summarize, there's going to be an input here, right? Subject to the weighted product. Then there's an activation function. And again, there's a weighted product. Then again, there's an activation function, right? This is the same simple approach for a neural network with single hidden layer. You can have as many hidden layers as possible, one, too many, right? So those many operations are going to happen in between, right? So I hope this is clear. This is a simple working of forward propagation. So this is called as forward propagation, where the values are propagated forward, right, to compute the final value as of the current set of weights, right? So it arbitrarily, the network arbitrarily assigns any random values to the weights and then computes the final output using this kind of a propagation, right? So I hope this is clear. Now, in the next videos, we'll talk about the different kinds of activation functions, right? Which basically are commonly used in neural networks, all right? So I hope this is useful, and I wish you all good luck in your studies. And if you have any questions, please comment in the comment box at the bottom of the video. Until then, Take care, bye bye, and see you in another episode. Thanks. If you like this video, please press the like button. For more such videos, subscribe to the channel. If you have suggestions for a new topic and would want to see a video made on that topic, please feel free to comment in the comment section below. Thanks for watching the video and see you in another video. Bye bye.